My name is Katharina Immer. I'm working at the Allegra ARC node. In this video, I will explain the calibration steps of ALMA data. The data received at the ALMA antennas have both amplitudes and phases. We want to integrate the observed signal in time and over a certain frequency range to increase the signal-to-noise ratio and the UV coverage. Thus, the phases of the correlated data must be zero and the amplitudes flat. Otherwise, the coherence is lost. Due to atmospherical and instrumental effects, the previous diagrams look more like this. In the amplitude versus frequency panel, we can see the bandpass shapes of the receiver. In the phase versus frequency panel, the instrumental delay leads to jumps between spectral windows and the atmosphere introduces a slope. The amplitude versus time is not flat if the source is observed at low elevations or has intrinsically varying flux. The atmosphere leads to rapidly wrapping phases with time. The data needs to be corrected for these effects. However, target sources are typically faint, so that the data are dominated by noise from the full primary beam of each antenna, so we need to rely on calibrators to calibrate the target data. There are typically three different types of calibrators that we observe in a project. These are the bandpass calibrator, the flux calibrator, and the gain calibrator. The first two can be anywhere in the sky, but the gain calibrator needs to be close to the target to apply a correction method called phase referencing. The bandpass and gain calibrators are strong point-like sources, typically quasars, while the flux calibrator is either a quasar whose flux density is being monitored or a solar system object for which a well-determined flux density model needs to exist. With the flux calibrator, the visibility amplitudes from the correlations are converted from arbitrary to physically meaningful values, similar to using standard stars in optical data calibration. These scaling factors are then applied to the other sources. We start the calibration with the purely instrumental effects. The bandpass shapes in the amplitude versus frequency panel have an instrumental origin and thus should remain constant during the observations. We can correct for them since the bandpass calibrator has a flat spectrum. This is comparable to applying a flat field correction optical data calibration. The jumps between spectral windows in the phase versus frequency panel is a pure instrumental effect due to different light paths. These are constant for the whole observation. The slope is an effect of the atmosphere. We can correct for these effects since the bandpass calibrator is a point source and thus should have zero phases as a function of frequency. These corrections are then applied to the other calibrators and the target. This is called bandpass and instrumental delay calibration. With the gain calibrator, we can calibrate the effects of the atmosphere on the phase stability. Since the gain calibrator is a point-like source, the phases should be zero both in frequency and time. During phase calibration, we fit the slope of the phases simultaneously in frequency and in time. These corrections are then applied to the gain calibrator itself to obtain flat phases at zero. If the amplitude of the gain calibrator is changing over the time of the observation, the self-calibration method can be used to obtain flat amplitudes. These methods are similar to using adaptive optics systems in optical astronomy. Once we obtain the corrections from the gain calibrator, we can interpolate them and apply them to the target. Now all observed sources are calibrated. After obtaining all calibration corrections, one should check the data of the calibrators before and after applying those corrections to verify that the amplitudes are flat and the phases zero in frequency and time. If this is the case, the calibration was successful.
This video is part of the ALMA Explained series, brought to you by the European ALMA Regional Center.